Okay, so welcome to the part 2 of the Parity based portfolio optimization. In the last lecture, we covered the what traditional methods are, what are the drawbacks, and then we started the introduction of this parity based portfolio optimization, in which we prefer that. So basically, we said that the risk contribution of all the assets should be equal, and that would be the true diversification, right? So, and then we define marginal risk contribution of asset I, which is defined as the change in risk of, change in the risk of the portfolio due to the change in the weight of the asset I. Okay, so that is the marginal risk contribution of asset I. And then the risk contribution of asset I will be given as weight of asset I into marginal risk contribution of asset I. Okay, and as you can see, the marginal risk contribution of asset I was Wi into sigma I square plus for all j not equal to I, weight of, so weight Wj into sigma Ij divided by sigma W. Okay. So this thing can also be written as, okay, so if you see this top term, okay, so this top term can also be written as the, like this. Okay, so this is the ith column of, so ith row basically, sorry, this is the ith row of sigma W matrix. So if you evaluate, if you see the ith row of this matrix, so this is basically variance and covariance matrix, and W is nothing but the weight matrix, right? So if you get the ith row of this matrix, this would be nothing but the numerator of the MRC. Okay, I just wanted to express it in this way as well. So basically, MRC of Ci can also be written as this one divided by, this is the risk, right? So this is nothing but risk. So basically, weight transpose into this. So MRC can also be written in this way as well. Okay. In the last lecture, we ended up the discussion with an asset case. Okay, and with the assumption that all so the correlations are equal basically. So basically rho ij equal to rho ik for any value of I and j, and so basically we assume that the correlation is rho only. Okay, now in this case let us assume that the volatilities of the asset are same. Okay, so volatilities are same, so volatilities of all the assets are same, basically sigma 1 equal to sigma 2 up to sigma n. Okay, so in this case if you try to solve for the weight which gives you the risk parity based portfolio, that means the RC1 equal to RC2 to RCn, that weight would be nothing but this one. Okay, up to n weight of k rho ik divided by so this is the way that would be, that you would be finding in this case in which volatilities are same. Okay, now when you see the volatilities are same, this is a basically case of endogeneity. Okay, what is endogeneity? Endogeneity refers to that situation where a variable is both influenced by and influences other variable in the system. So you see this is Wi, and here as well you will find Wi in the result. So basically you want to find Wi, but for that, for in the expression of Wi itself is appearing in the expression of Wi, right? So this is a case of endogeneity, and you won't be able to solve this equation. So that is why when the complexity start increasing, for example in a general case when even volatilities are not same, then in this case you will get a endogeneity solution, you won't get a closed form solution. Okay, so that is why we have to resort for numerical solution, and numerical solution basically gives you the result to find, so basically they help you to solve the problem. Okay, so let us discuss two numerical solution of the risk parity based portfolio optimization, and that will be the end of the lecture. So why do we need numerical method? Because we won't be able to solve for a complex case, we won't be able to find out the weight just algebraically, right? So that is the case. So you won't be able to find the weight just like we did for two asset case, or just like we did for the case when they had the same correlation, right? So it was easy then, but it won't be easy when the volatility are same, or basically when nothing is same. Basically a simple case. Okay, so numerical solution. The method 1. Okay, so see, the inherent assumption is that we are assuming a risk parity based portfolio, and so in this case the weight W, so in this case the weight W would be given as arc minimum of FW. Okay, I will explain it, don't worry. Under the condition that the total summation of weight are 1, so this is nothing but it is a weight matrix, right? So W1 is nothing but, so it is like W1 1 1 1, and then W1 W2 Wn is equal to 1. So this is nothing but the condition that the summation of all term should be equal to 1, right? Summation of all asset as weight of all assets should be equal to 1, and then the other condition is all W should be between 0 to 1. Okay, so now what is FW? FW in this case is nothing but summation from I to n, from j equal to 1 to n, okay, xi into, this is the marginal risk component part, right? So basically this is FW. So what is this? This term is nothing but you want to equate this term to 0, that this is the risk contribution. So this is nothing but RC1 into FW. So this is nothing but RC1 into sigma W, and this is nothing but RC2 into sigma W, right? So basically what you are trying to achieve is RC1 into sigma W minus RC2 into sigma W equal to 0. So you are basically trying to find out a solution for RC1 minus RC2, sigma 1 basically will be here, equal to 0. So you are basically trying to find out a solution for which RC1 is equal to RC2. So basically FW, so you want to minimize the value of FW. So you want to find out for what value of W basically this FW term would be equal. Okay, so in this case the existence of a portfolio, risk parity based portfolio, so basically it is also known as the existence of risk parity based portfolio optimization is confirmed. When will the existence of risk parity will be confirmed? When this term minus this term, so this term and this term would be equal, right? Then the risk contribution would be equal. So when FW is equal to 0. So you want to find the numerical solution. So FW, so you want to make FW 0, and in numerical solution FW cannot be exactly 0, but you want to make it as close to 0 as you can. So this statement mean what is the weight in the case when we want to minimize FW. So we want to make FW as small as we can, given the condition that sum of all weights are 1, and basically all weights are between 0 to 1, and then FW in this case is defined like this. Okay, so it is nothing but the so we are subtracting all the risk contribution term. Okay, so this is FW. So this is how we can try out finding the solution, okay, for the weight W. So you can see this term FW is nothing but it will be 0 when all the risk contributions are equal. Okay, so that is the core purpose of this numerical solution. Okay, and the other numerical method, so the inherent theory behind this numerical method is risk parity only, because you want to, so because FW will be because we want to minimize FW, and FW will be 0 only when all the risk contributions are equal. So so basically the risk parity based portfolio optimization, right? And then one another risk parity based portfolio technique is where the weight y would be nothing but minimum of the variance term. So just a minute. Minimum of the variance term, and under the condition that for I equal to 1 to n, the ln yi should be greater than c, and all the basically weight should be greater than equal to 0, right? And see here c is an arbitrary constant, okay? And then the portfolio would be given as, portfolio weight would be given as the normalized y, right? So it would be wi star into I equal to 1 to n or y, okay? So it is the summation for all I. So this is the weight of asset I in this case. Now this is, so if you try to solve it using Lagrange's method, okay, you will see that the inherent assumption, so this would be minimum only when you are following a risk parity based portfolio. So this is also an example of risk parity based portfolio. So when you solve it and when you get the weight W, that weight will also correspond to the risk parity based portfolio. So that weight will give you the equal risk contribution. So you can try it and see proving it. So basically I will be attaching a research paper along with this video, and then in that research paper you can see that this indeed correspond to a risk parity based portfolio, and you can try solving it numerically. So you can try solving this numerical optimization problem to solve for the weight Wi, okay? So this is the end of the lecture, risk parity based portfolio optimization. So these two methods can be used to solve for the weight W numerically for the complex cases when volatilities are same or when nothing is same, basically everything is different. In that case you won't be able to solve problem algebraically, you need to solve it using numerical optimization method, okay? So that is the end of the lecture. Thank you. Please go through the research paper once that I will be uploading along with this video. That will help you to learn a lot from this lecture.